Today we're going to talk about the pressure versus temperature tables. This is for saturated water. So what this table tells us, it's at the boiling point of every water at different temperatures. So as you can see, I have one atmosphere, which is 101.3 kilopascals, which is around 100 megapascals. Water boils at 99.63. So then we could use these tables to find the state of different the state of liquid in different situations. So for example, if somebody tells me at 0.1 megapascals there's a liquid at 130 degrees, then I would know that, okay, it's not here, it should be in the superheated table. So I'll go to the superheated table and I'll go to 0.1 megapascals right here. Go to the 120, between 150 and 100. These are the specific volume, the internal energy, the enthalpy, and entropy. So using these values, I could use them to solve problems like based on saturated water. If we need to find the steam enthalpy, like when it's fully steam, what's the enthalpy of it? And no, it's not only for superheated water. We also have a table for refrigerants. So these tables are specified for the specific elements that are used in the problem. So for example, in this case, if we're using a refrigerant, then we should go to the refrigerant pressure versus temperature table, and we find the values here. For example, if we go back to the superheated, the temperature was 120 degrees. It was between 100 and 150. So I'll show you how you could use interpolation and find the exact values at between 100 and 150.
How to solve for a specific volume for pressure is equal to 0.1 megapascals and T is equal to 120 degrees Celsius. So we don't know what we're trying. So we're trying to find X over here. We know the specific volume at 100 degrees and the specific volume at 150 degrees by looking at the superheated table. Linear interpolation, here's the formula right here, which is specific volume at 120, which we're trying to find, so minus specific volume at 100 degrees over V is equal to 150 degrees Celsius minus V at 100 degrees Celsius. That's going to be equal to the temperature we're looking for. Temperature we're going to look the specific volume for, 120, minus the lowest over the highest one, which is 150, minus 100. So let's plug in these values right here into this. Now we got X minus 1.6958 over 1.9364 minus 1.6958, which is equal to 120 minus 100 over 150 minus 100. You solve for X, and that is your specific volume, 1.79204 meters cubed per kilogram.